Hello students, so in this lecture we are going to discuss about the mechanical properties associated with the nature of crystal. That means if it is a polycrystal, how it is going to behave differently than its single crystal counterpart in terms of mechanical property. Now at room temperature, the ductility exhibited by a second crystal does not extend to polycrystals. In fact, a polycrystal of grain size less than, say, a polycrystal having a grain size which is less than 0.5 millimeters, they are effectively brittle. So ductility of the single crystals are much more than the polycrystal at room temperature. This behavior, which is exhibited by many ceramics, is explained in terms of limitations on slip, which do not exist in most metals. So, when we say a polycrystal, we are basically referring here to ceramic materials, and there is a concept of limitations of slip. Which is mainly found in ceramic materials. Now, according to von Mises, in order to produce an arbitrary change in shape, we need to, in the crystalline material, five independent slip systems must operate. It says us that words. In order to produce any arbitrary change in shape of the crystalline materials, there are five independent slip systems must operate. For that, five independent slip systems must operate. Now, a slip system is independent. By a slip system, we mean that has to be a perfect direction. It is a combination of a direction and a plane. So you can write a slip system is actually a direction and a plane and a set of directions through which the dislocation can move most efficiently. Every crystal structure has got its own slip system. Now, a slip system is independent if it produces slip which cannot be achieved by any combination of slip on the other system. So, slip system is independent if it produces a slip which cannot be achieved by any combination of slip on the other system. Now, the basis of the argument is that an arbitrary shape change can be described by the 6 independent components of the strain tensor. So, what we are dealing here is if there is a shape change taking place this change is due to the six independent components of strain tensor. That means XX, YY, ZZ. Do it in a different way. XX, YY, ZZ, and we have got XY, XZ. This is again YX. This is again YZ. This is ZX, and this is ZY. Why it is called 6? Because we are considering XY and YX as same. Similarly, ZY and ZX as same, and ZX and XZ as same, ZY and ZY and same. So that effectively there are 6 components. So a shape change is can be described by these 6 components. So these are the 3 normal strains, the diagonal ones, and the rest are the shear strains. However, here volume is conserved during the plastic deformation by the slip. So you can say that since the volume is conserved during plastic deformation by slip, and the normal strains must sum to 0 so that only 5 of the components are independent. So another concept is that the normal strains must add to 0. So out of 6 now, if we consider this constraint, then we have 5 of the components are independent. So we can say that 5 of the components are now independent because they have been bound by this constraint. Now, shear produced by one slip system determines the value of one of the components of the strain tensor. So shear produced by one system, it determines the value of one of the components of the strain tensor. Determines the value of one of the components of the strain tensor. So the 5 independent slip systems are needed to produce an arbitrary change in shape. So this is the 5 systems that we have, von Masses has talked about. Now in polycrystalline materials, if a grain is not free to change its shape, strain incompatibilities which develop at the boundaries with other grains would produce high local stress and fracture. So this is an important point. So if the case is such that in the case of polycrystals, if a grain is not free to change its shape, if a grain is not free to change its shape, so this may lead to strain incompatibilities at the grain boundaries, which with other grains, and will produce local stress and fracture, which will eventually lead to a local stress followed by fracture. Now, metallic materials generally possess 5 requisite slip systems and are thus ductile in both semicrystal and polycrystal forms. However, ceramics do not. So, metallic metals, they have these 5 required slip systems and are thus ductile in both crystal and polycrystalline forms. Therefore, they are ductile in both single and polycrystalline forms. This is not the case for the case of ceramics, whereas in case of rock salt NaCl, only 2 of the 6 physically distinct slip systems operate. So in the case of rock salt, that is NaCl, which is considered to be the ionic ceramic material having the lowest or having no electrostatic faults, even in that system, 2 out of 5 slip systems, they work. So of course it is at room temperature, so it explains why there is a ductility loss in the case of ceramics. Now, from a microstructural standpoint, the transition from brittle to ductile behavior often correlated with the onset of base slip, that is a slip which is not confined to a single slip plane. Now in rock salt, wavy slip, so we have a new concept of something called wavy slip. Now this slip is not confined to any plane. So this is a slip which is not confined to a single slip plane. This is called a wavy slip. And rock salt wavy slip becomes possible at high temperature. So in rock salt, this wavy slip is possible at high temperatures because of the activation of the secondary slip system, and this is mainly due to the activation of secondary slip system. However, studies show that it is not the onset of the wavy slip but the disappearance of the straight slips that is the reason. But interestingly, studies show that it is not the wavy slip but the disappearance of the straight slips which gives rise to ductility in a rock salt structure, giving rise to a slight amount of ductility in rock salt or any ceramic having little bit of plasticity for that matter. Thus, ductility is limited by the nucleation of cracks by stress concentrated developed at the intersection of straight slip bands and grain boundaries. We can include that. And ductility is limited by the nucleation of cracks by stress concentrations developed at the intersection of straight slip bands and grain boundaries. So this is important. At the intersection of straight slip bands and grain boundaries. So we plot percentage elongation, which is measure of ductility, with respect to temperature given in degree centigrade. So we get a plot like this. This is 100, and this is 200, this is 300, and this is for a rock salt structure, KCl. So we can see that there is a certain increase in ductility at a certain temperature. This is mainly because of the fact that there is a disappearance of dislocations taking place at a certain specific temperature. And at room temperature, ductility in case of ceramics is very low. So this temperature has to be reached if a ceramic material has to be made ductile.